Let us talk about this problem. We are given a binary tree. We need to count how many nodes in it. That's what the size of a given binary tree is. Let's see this tree. We have 5 nodes in it, so size is 5. We have 3 nodes in it, so size is 3. In this binary tree, we have 6 nodes, so output is 6. If the input tree is empty, then output is 0. Now please pause this video and try to write down a code that returns size of a given binary tree. Here is recursive implementation to find size of a given binary tree. Let's see and understand how does this code work. We have a base case which checks if root is null, then we return 0. Otherwise, we return 1 plus get size for left subtree plus get size for right subtree. So we have passed root as of this binary tree. What are we doing? We are getting recursively size of this subtree, this left subtree, and we are getting recursively size of this right subtree. So this recursive call will return 3. This recursive call will get 2. We'll add 3 and 2 and add 1 to it. So we get 3 plus 2 plus 1, 6. That's how this recursive code works. Let's now understand it step by step. How does this work step by step? So we initially pass root of this tree. Now we go inside this function and check if root is null or not. We come here, right? In C++ and Java here, we check if root is null or not. Root is not null. So what do? We make a recursive call for left subtree, and then we make a recursive call for right subtree, and we add their results and add 1 to it. So first thing we are doing is making a recursive call for left subtree. So we make a recursive call for left subtree. When you make a recursive call for left subtree, the function begins execution from first line again, and again this becomes your new root, and the first thing that happens is it is checked whether root is null or not. Root is not null, so it again makes a recursive call for its left subtree. So this is a new root. And this also is not null, so it's also going to make a recursive call for its left subtree. And this time root is null, right? Its left child is null. So when root is null, you fall into the base case and you return 0 to the parent call. So the call for null returns 0 to this call. Now this is going to call recursively for right subtree, and right is also null. So this call is also going to return 0. Now once left and right children for this have done their execution, they have returned the value. This function, which was called for 40, it is going to resume its execution, and it's going to add these two values, and it's going to add 1 to it. It's basically going to execute this part. So it has executed this, it has executed this, and now it's going to take these two values and going to add 1 to it, and it's going to return. So what does it return to its parent? It returns 0 plus 0 plus 1, right? Or you can say 1 plus 0 plus 0, which is 1. Now the parent gets the control back, and its left call is done. It's going to now call for the right child. And right child, when called, your root becomes this node. This is going to again begin execution from the first line, and in the first line it's going to check if root is null or not, and root is not null, so it's going to call for the left subtree, which is null. And when you call for the left subtree, again the first line is being executed, and you fall into the base case and you return 0. So the left for this returns 0 to it, and right for this also returns 0 because that is also null. And what this function is going to do, it's going to add 0, 0 to it. So it's going to return 1 to its parent, right? So this has returned 1 to its parent, and this has also returned 1 to its parent. Now the control comes to the parent, and parent get this value 1, get this value 1, and it adds 1 to the returned values. So it's going to return 1 plus 1 plus 1 equal to 3 to its parent, right? Get left plus get right plus add 1 to it. So it's going to return 3, right? And once this function has returned 3, the control is going to come back to here, and this is going to now call for the right child. And what right child will do? Right child will again call for the left child, and left child is null. So left child call is going to give it 0. Now it's going to make a call for the right child. Now this is your new root, and you will begin execution from the first line whenever recursion happens. And when you call for the left of it, it's going to return 0. When you call for the right of it, it's going to return 0. So it's going to return 1 plus 0 to its parent, which is 1. And its parent got the value from 0, got value 0 from the left side, and got value 1 from the right side. So it's going to return 1 plus 0 plus 1 to its parent, right? 1 plus left value plus right value. And now control comes back to this. Its left is over, its right is over. And what this function is going to do, it's going to return 1 plus 3 plus 2. This value returned by this right call is 2. So it's going to add the value of the left call, add the value of the right call, and it's going to add 1 to it. So it's going to return 6. And that's how you get the correct size of a binary tree using this recursive function. Here is one more diagram to make the recursion understanding more clear. We started with node 10. This was our initial root. And then it called for its left subtree, which called for its left subtree, which called for its left subtree. And this call returned 0 to the parent. And then it called for the right subtree, and right subtree call also returned 0. So what this did, this function call added 0, 0 and added 1 and returned 1 to its parent. And now this was called, and this called for left subtree and right subtree. Both of these returned 0. This also returned 0 and this also returned 0. So what this call did, it added 1 to the 0, 0 and added 1 to this parent. So what parent did, it added 1, 1 and added 1 and returned 3 to its parent, right? So parent, the main code, finished with the left call. Now it made a call for the right subtree. And when it made a call for the right subtree called for the null first, which immediately returned 0. Then it called for 60, which made 2 calls for left and right children. And these 2 calls returned 0, 0. So what it did, it added 0, 0 and added 1 to it. So it returned 1 to its parent. Now what parent did, added 1 to 1 and 0. So 1 plus 0 plus 1, 2. So it returned 2 to its parent. What parent did, 2 plus 3 plus 1. So returned 6 to the caller, which is your final output. Let us do analysis of this code. This code simply does a traversal of the binary tree. So the time complexity is simply big O of n, because every node is visited exactly once, and there is big O of 1 computation or constant computation that we do for every node. We simply add 3 values, right? So its overall time complexity is big O of n. Auxiliary space required for this solution is big O of h. How is it big O of h? If you see the recursion call stack, first a function call will go for this root will go into the recursion call stack, then this will go, then this will go. So your recursion call stack will have function call for 10, then 20, then 40. Then it will have for null. And once this null call returns, the control will go back to 40 and it will call for the right child, which is again null. So once this null is also done, control will go back to 40. 40 will compute its value and give the control back to the parent. Now the control goes back to parent, it will call for 50, right? And 50 will call for left null, then right null. And then once 50 is over, the control will go back to 20. Then 20 will go out of the stack. Then 30 will come into the function call stack. And 30 will first push null and then it will push 60. And when you push 60, 60 is going to push first null, left null and then right null. If you take a look at this execution process, you can notice that at any moment you have number of active function calls proportional to height of this binary tree. In fact, maximum number of function calls that are there at any moment is height of this binary tree plus 1. If for example, in this case, height is 3, and we saw that when we were making a call for 10, 20, 40 and null, we had 4 function calls into it. Even now, if you see, 50 is going to make a left call for left subtree, which is null. So that's the maximum number of function calls that you have at any moment in the function call stack. So auxiliary space required for this solution is big O of h. We can also understand auxiliary space with this diagram. You know, when you call for this goes into the function call stack, then this goes, then this goes, then this goes. And once it returns, then this goes. So at any moment, you have number of function calls into the function call stack equal to height of this tree that we have drawn, this recursion tree with this root, right? At any moment, you will have at most 4 functions in the function call stack. First you will have these 4, then you will have these 4, then you will have these 4 functions and so on. And when you come here, you will have actually 1, 2, 3 functions into the function call stack. So at most you have 4 functions. This problem solution that we have discussed, it's a recursive solution. We can solve this problem iteratively also. An iterative solution is to use level order traversal. We simply use a queue and we have a loop inside this level order traversal that says while queue is not empty. So we initialize our counter as 0 and inside this loop we keep on incrementing the count. And at the end we simply return the count. So iterative solution can also be written for finding size of binary tree. Time complexity of iterative solution will also be big O of n. However, auxiliary space differs when you talk about iterative solution. In recursive solution, the auxiliary space is big O of h. In iterative solution, the auxiliary space is big O of width of the binary tree, because at any moment you will have a complete level into the queue when you are doing an iterative traversal of binary tree.